This meeting is being recorded.
Let's move that over. Hi, good afternoon, everybody. Welcome back to data mining. A couple of quick announcements for us before we get started in earnest today. So vast majority of you will be doing the exam, oral exam with me this week, Thursday or Friday. Last Friday, we had a pretty good, I think, review session. A lot of people showed up. A lot of people asked really good questions about things. So based on that, I'm willing to clear out more time from my schedule this week to offer more exam prep if you would like. Really the only time, though, that I'll be available this week is tomorrow, immediately after the office hours time from 11 a.m. to 12 p.m. If you would like that, an extra review session tomorrow, 11 a.m. to 12 p.m. We'll have the same sort of thing here. I just need somebody to make a GitHub issue asking for it, and at least 3 other people replying to that say they will attend. And if you do that, then I will cancel the thing that I currently have there and schedule you all there instead. Another announcement or exam-ish thing is, again, one of the common failure modes of students on these oral exams is that you study a lot for the material. You know the material really well, but you haven't practiced actually explaining it out loud to people or writing something on the whiteboard about what you're going to talk about. So please practice actually on a whiteboard, preferably in front of somebody else, but at least on a whiteboard. And definitely your intro little speech, the 2 to 5 minute speech about either the power method or the exponentially accelerated power method. That's something that you should have practiced. I would suggest 2 or 3 times, but definitely at least once on the whiteboard, writing that out, talking as you're writing, so that when you come to the exam in my office and are actually doing it, it's not the first time that you're doing that in front of somebody else. Any questions about anything administrative related to the exam? Yes. Question is, will there still be the normal 9 to 11 office hour time tomorrow and Tuesday? And the answer is yes. Also on Friday, there will still be the normal 9 to 11 office hours time. And you're certainly all welcome to come and ask questions about the exam or anything else, but know that I will not prioritize talking about the exam stuff. So if people have questions on, say, the homework assignment, the coding stuff, then I will probably prioritize that over exam specific stuff. And also my other class has their own homework assignments as well, and there will likely be people from the other class there that will get my attention. So if you want a time specifically only for the exam stuff, then this is the time I'm available, and this is the thing to do for that. Good question. Maybe since I just mentioned the homework assignment, I'll say that the nominal due date, again, the original due date was yesterday. And a handful of students have submitted yesterday. Everybody who did submit got full credit on it. You're not required, though. If you haven't done it, you're not behind. You have until the following next week, Sunday, to submit it without getting any sort of late penalty. I recommend, again, completing it before you do the final exam so that the problems that it's asking you to do help build some intuition about these different hyperparameters like alpha, why it's important, and that can come up on the final exam. But if you have to pick between doing the homework or studying for the final exam, you should study for the final exam because that will happen first, and then afterwards you can do the homework. Any other questions, anything administrative? Yes. Okay. I have seen the pull request. Yeah, we can talk about that more. Okay. Yeah, Yeah, so for the homework assignment, well, let's see. Yeah, I'll go ahead and come over here to the pull requests tab. The specific thing. I originally started this homework assignment, I don't know, I guess 4 years ago is the first time that it was given. And so PyTorch had a different interface back then. And click that link. And so I used this torch.sparse.float tensor thing. And I guess they have replaced that with this as the correct function to use. This one should likely still work in the newest versions of PyTorch, just give you warnings about something being deprecated. Deprecated means that something still exists and still has the same exact functionality, but you should stop using it because in the future they will remove it. So the reason why this has been deprecated and replaced with sparse COO tensor is because there are now other formats besides this COO format that PyTorch supports for sparse tensors. They have, in some situations, better constant factors, but everything that we have said has been specific to COO tensors, but also applies to every other possible sparse format. Deprecation warnings, things that you can safely ignore for like homework assignments, but the sort of thing in the future that you, if you're maintaining code for a long period of time, would want to fix. And speaking about maintaining code for a long period of time and looking at GitHub here for a bit, one of the things that I did over the weekend, we were just talking about weekend stuff too, is but I went to a birthday party at Chuck E. Cheese and for my 6-year-old. And I was talking to one of the other parents there who I'd never met him before, but he happens to work as a machine learning engineer at a company that does sort of statistics analysis for like ESPN and other channels that air sports types of things. And I always, every time I randomly encounter a engineer out in the wild, I always ask them what is the like one thing that students who you hire, they don't know that they should know when they graduate. And this person's answer, like 80% of the answers that I get from people, was that students don't use Git. They don't know how to use Git. And that's not the focus of this class, using Git, but we do a lot of things with Git and GitHub in this class, and the motivation for that is, again, to help prepare you for future job situations, make you good candidates for future jobs. And so this is a great example of using GitHub, Git to update the repository with some older information, and now it's going to be available to everybody. That's a big aside. Any other administrative sort of questions about anything? Okay, today we will be going back to the Notes 1 packet, this packet over here, covering this a little bit more, and we'll be going at least what I consider to be a relatively slow pace today. Doing a lot of filling in details about things. And one of the motivations for going at a slower pace today is that, again, I know that everybody is very preoccupied with the PageRank exam stuff coming up. So whatever we talk about today is just like not the most important thing in your head, in your mind. So we will not try to cover too much today, get you so that you can still focus on the PageRank stuff. So we're just gonna, no new notes packet. We'll just be focusing on this notes packet 1 right here. I will also be doing some stuff with a blank sheet of paper, drawing some extra pictures over here that's not related to problems in the notes. So if you don't have blank pieces of paper and you would like some, I brought some up front and you can come pick them up. Last thing, yes, that is all the announcements stuff. So I'm going to take a look. Let's do some review looking at the actual textbook here. And again, these note packets designed to follow the textbook very, very closely about things, the problems that are related to textbook things. I will provide you exact page numbers or section numbers about where those problems come from. And one of the problems we did last time was about this figure 1.2 right here, this basic setup of the learning problem. So just to review for us, we have some unknown target function, which will always be f in in this class, always be f, and we are generating training samples somehow from this f function. Again, our assumption so far is that this x of n, maybe I'll go ahead and write this. Oh, I can't write it in. Our assumption so far is that the x's are generated, or the y's are generated from x by applying f. I wrote that out last time in our picture. It's not explicitly in the picture here yet, though. And then we have a learning algorithm and a hypothesis set generating this final hypothesis G. G is the thing that we are learning, and we want G to be approximately equal to F. We're going to see some more pictures related to this picture next time, next class section that starts introducing statistics about the learning problem. And we'll be needing statistics to know exactly why G is approximately equal to F, or under what situations we can guarantee that G is approximately equal to F. But at this point, with these sort of 5 boxes right here, 4 boxes in one circle, this is all the information we need to talk about the runtimes of learning algorithms. Last time, we also started talking about the perceptron algorithm. So scrolling down here, this perceptron is our first example, and we saw a handful of different ways that you can write out this hypothesis class right here. So this 1.1 formula right here, equation 1.1, this is not an algorithm. This is a hypothesis class. Again, the hypothesis class is something that a lot of textbooks, especially at the undergraduate level, sort of ignore. But we'll be talking a lot about this hypothesis class down here, or hypothesis set, the word class and set synonyms for our purposes. And a lot of the statistical and runtime analysis that we do will be based off of this hypothesis class down here. So this is going to be a very, very important thing for us. And we saw last time that there were many different ways of writing out this hypothesis class. We saw 3 different types of formulas, ways of writing this out. One, there was a really good question after class about the subscripts over here I want to highlight. Notice here in equation 1.1 that this W and this X, these subscripts, Wi, X sub I, this W and this X are not bold. These are only in italics. When you see something that is not bold, that means that it is going to be not a vector, but a scalar. So this W sub I is a scalar, where it is the ith index of vector W. This is confusing because up here in the notation, we also have X sub number, Y sub number, like X1, Y1, X2, Y2, and so on. And these, the X's up here are bolded. And so you know, because it's bolded, it is not an index into the vector, it is the actual number of the vector itself. So this X sub 1 is the training example number 1, an entire vector of itself. But down here, this X sub I right here, X1, 2, and 3, because it's not bolded, this is the index into the vector I. It's a very common notation to see in machine learning things or numerical things in general about the difference between bolding and non-bolding text. I find it very annoying because it's impossible to reproduce in handwriting about bolding a variable versus non-bolding a variable, but it's a very common thing to do. Okay, and then the last thing that we covered last time is we started visualizing some of these hypothesis classes. Every time you have a hypothesis class, the first thing that you want to do is, in order to understand it, is actually plot out some of these hypothesis classes. And in this picture right here, we have, at the very end of class, I drew some pictures that were very similar to this. But on the left and right-hand side, we have the same data sets here. These circles and these X's are all different data points. The location that they're at is the X coordinate, the X vector. And whether it's a circle or an X is the Y value. The perceptron hypothesis class is often called a linear hypothesis class because that formula that we saw above results in straight lines through the data space like this. This graph that we're looking at, where we're looking at data points on a 2-dimensional plot, is sometimes called the data space, and the perceptron draws straight lines through the data space. On the left-hand side, we can see that this is an example of a bad perceptron because there are some misclassified data points that the way these pictures are drawn, the darker shaded area is supposed to be the circles and the lighter shaded area is supposed to be the X's. And so if we had a perceptron that looked like this, we have some misclassified data. The circle here is on the wrong side and the X is over here on the wrong side. But on the right-hand side, this is an example of a good perceptron for this data, because now all the X's are on the left-hand side and all the circles on the right-hand side with no misclassified data. What we're going to talk about today is two things. First, we're going to go into more detail about how these visualizations are done. And then the second thing is we're going to go into computationally what an algorithm looks like that is going to give us a good, perfectly classified data set, like on the right-hand side, instead of something on the left-hand side. So two things. First, visually understanding exactly what's going on in these plots, how it relates to those formulas up above. And then secondly, computationally, what the algorithm is that does this. Any questions about anything we did last time or where we're going today? Question, yes.
What makes this hypothesis class linear?
Question is, what exactly makes this hypothesis class linear? It's a really great question. If I scroll down a little bit, there's going to be this alternative version of the hypothesis class right here. And the first answer to this question about what makes this hypothesis class linear is that there is an inner product inside of it. Anytime the hypothesis class is somehow like defined by an inner product, we call that a linear hypothesis class. Inner products and linear things have a very close relationship with each other, which we will explore a little bit here in more detail in just a minute. The second thing about why we call this a linear hypothesis class is because when we actually plot this line, these lines are sometimes called, well, they have many names. One is a decision boundary, another is a separating hyperplane. But somehow, whatever, like this line here that we're plotting that separates the circles from the X's, it happens to be a straight line for the perceptron. And no matter what values of W we select, so this W here is the hyperparameter for our perceptron hypothesis class. We can see that the X over here is something that is given to us, it is passed in. The W is the thing that determines exactly what our function is going to do. That W value, no matter what W's we select, we're going to get a different line over here, and it's always going to be a straight line. A nonlinear hypothesis class, which we will see many examples of later on, a nonlinear hypothesis class will give us some sort of squiggly line, like a parabola or a circle or something like that. So it's a good question. We'll explore that in more detail here in just a second when we talk about exactly how these plots relate to those hypothesis classes. Other questions so far? Okay, then I'm going to switch over to my blank sheet of paper here, and we are going to start by drawing out exactly how, like, from the equations, how do we get these lines over here? How do we get these decision boundaries? How do we get these separating hyperplanes? And I'm going to point out, as we do this, some common misconceptions. The stuff that we do today, especially on this, this blank piece of paper that I have up here, this is not something that is going to be explicitly asked of you on a midterm or final exam. The midterm and final exams are all going to be based just on the stuff in the notes packets. But this is going to help give you some, I think, strong intuition for the some of the linear algebra stuff that you're expected to know, that's like the background required material for this class, but maybe has gotten weak for you since you took linear algebra. So this is a good thing to understand for the other problems, but if you don't fully understand 100% of it, that's okay. The purpose of this is to give you like good background information. Okay, and what we're doing here is we are visualizing the perceptron. Anytime we're visualizing any sort of learning model or just algorithm in high dimensions, it's always good to start with the simplest possible case of a one-dimensional problem. So that's what we will do here. One dimensions. And when something is one dimensions, in our textbook, the D is the number of dimensions. And so our x values are all contained in r to the d, which is now equal just to r. And similarly, our weights vector is always contained in the same number of dimensions, r to the d, which is also just equal to r for us. And I'm going to draw a plot over here next of some example data and what it might look like in one dimension. Actually, I'll also draw what our hypothesis class looks like. So h of x equals w sub 1, x sub 1 plus b. This right here is coming from equation 1.1 in the textbook, equation 1.1. And all I've done is simplify it so that it has the exact number of dimensions that we're using. I'm going to jump over to the textbook just for a second so we can find equation 1.1 right here. I've just rewritten equation 1.1 where this summation d equals 1. So there's only one term right here. And we get w1 x1 plus b. I guess I also forgot this sign value right there. So let me add that in. H of x equals, I'll do it in red since I forgot it, SIGN of all of that. And then let's go with purple for our data points. One more thing on this x-axis, I'm going to draw a 0 point right here. And the label for this, these are the x sub 1 values. So this is the this x right here, this x sub 1, this is intended to be non-bold, which means that these are the the coordinates themselves. Like x sub 1 here is the first coordinate of all the x vectors, and it is not vector 1. It is the coordinate 1. And I'll draw these data points as being a bunch of pluses over here. All of these pluses, again, are directly on the axis right here. Do some pluses like that, and then some minuses like that. The location of these pluses and the location of these minuses is the x sub 1 value. If we have a plus right here, this indicates that the y value is +1. And if we have a minus over here, this indicates that the y value is a -1. Y equals -1. Are there any questions so far about what I have drawn? Ambika?
So when we're talking about like our data set of n from like x to the y or like those, so we're saying like x goes to value.
Currently, that is correct. Our x's, our input data points, are just a single scalar values because we're in one dimension right here. So we're visualizing this in the simplest possible case, and like visualizing a 100-dimensional problem, a little bit harder than one-dimensional. So we're starting with one dimensions, and then we'll see how to generalize this to cases that are more interesting. Okay, let's go orange here for the next part. So far what I've visualized is just the x's, the data points themselves, the x's and the y's. Now what I'm going to visualize is the w value and the b value. So w and b here in orange. And I'm going to start that with this, adding a new axis onto my graph right here. And I'm going to call all of this stuff inside the sign right here. We need to come up with just some name for that. If this is somehow like related to the y value, because our h of x, again, is what is going to be our predicted y value. And so this is somehow related to the y value. A common way of saying something is related to something else is just to take the value over here and put a squiggle on it. So I'm going to call these the y squiggles, the y squiggle axis. This is sometimes, let's see, like on your keyboard, this is often pronounced as the tilde character. People will call this y tilde or y squiggle. Those are the two common names for this particular annotation. And the b and the w values are what I'm going to plot. So I'm going to use a b value right here of maybe this is like b equals +1. I'll call this, that's the b equals 1 location. And now I'm going to draw a line through here with slope of this line. Slope of that line is equal to w, which is, we'll call it -1. We don't know, there's no like units on here, so it's hard to say exactly what it is, but we definitely know this is a negative slope. And looking down over here, the reason, like again, where this linear intuition is coming from, why we're calling this a linear classifier, is because in one line, if we plot like y squiggle equals mx plus b, w1x plus b, we get our standard straight line formula for things. And we do the sign of this, we're saying that anything that is below this line is going to get a plus associated with it, and anything that is above this line is going to get a minus associated with it. This particular plot is not yet the same sort of plot that we're looking at in the book. The book has no plots that look anything like this, where there's an explicit access for this b variable and this y tilde. The book has no plots that look like this. This is something totally different. But we're going to use this to get us some intuition for the plot that the book has. Any questions so far? Okay. So I want to point out some potential mistakes right here. So here, when we look at the pluses and the minuses, the point where our orange line right here, the point where this line, the y tilde line, maybe I'll actually label this too as y tilde somewhere, that y tilde line. The point where this crosses the x-axis, this is our threshold where we are determining whether things are positive or negative based on this threshold. The textbook specifically calls this hold at different points in the book. And really, like in some sense, the thing that we're interested in is just this number right here. This number, though, is not easy to directly predict or directly visualize based on just our W and our B values. I mean, there's a relationship to it, but it's not easy to directly visualize it. And in particular, one of the common mistakes that students make is that you assume that this distance right here, the threshold to the origin, you assume that this must be W, but that is not the case. So this is a common mistake right here. This is not W. The thing I wrote is true. The mistake that students make is thinking that this is W. Okay. I'm going to do another plot now here of a different way of visualizing all the same information. Before I do that, though, I'm going to go. The y tilde is everything inside the sign. So y tilde is equal to w1 x1 plus b. That like standard equation of a straight line. I'll go red now. The next picture that I'm going to draw is closer to the picture that is in the actual textbook. One of the things that the textbook does is they say, okay, and we did this a little bit last time, we said that we can rewrite h of x as this new thing of sine w transpose x. And I want to talk about how this w right here and this x right here relate to this w and x right here. The textbook uses the exact same letters, w and x in both locations. Right now, though, I'm going to make this a w prime and an x prime. Maybe I'll do squiggles. That'll be easier to. No, we're going to do primes. W prime and x prime. And we're going to see how exactly do w prime and x prime relate to these w1s and x1s. So w prime is defined, if we define it, as w1, comma 1, and then x prime to be equal to x1, x1, like that. sorry, this should be W1b and x prime x11. If we define these two vectors now, these two vectors as this with this substitution, then this equation right here, when we substitute in these values, is exactly the same as this equation up here. Again, because this is like a standard procedure mechanical thing to do, we often just write W and X with the same letter names as we do up here, understanding that there's this mild transformation adding a new dimension over here. So technically down here, the dimension of this W prime is now in R to the D plus 1, which is equal to R to the D. And that's also true for the X prime. Sorry, that's not equal to R to the D, that's equal to R to the 2 in this case. And the textbook often does not include this plus 1 down here. I will often not include this plus 1 down here and just call these d-dimensional vectors, but they have this additional thing added to them. What we're going to plot over here now is our x1 values and our x2 values over here. So this is a different plot than the plot up above. The x-axis is the same. They're both x1 values, but now the y-axis is going to be different. And that will be important. So now our x values will all be the same. Again, a bunch of pluses over here. Did I have 3 on the left? Yeah, 3 on the left and 2 on the right. And then 3 negatives over here. And the y values are all equal to 1. The separating hyperplane in this two-dimensional space now, what it looks like. What color did I use it there? I used orange. We'll stay with orange. The separating hyperplane now looks like this going through the origin. Now looks like this going through the origin with pluses over here and minuses over here. This is the y tilde value, which is now y tilde equals W prime transpose X prime. And so this is, I've plotted the same exact information, just a different way of visualizing it. One of the things that you might remember from linear algebra is that if you have an equation like this, the terms will always go through the origin. And so this is going through the origin right here. Another thing that you might remember from linear algebra is that anytime you have a hyperplane can be uniquely determined by a vector that is perpendicular to the hyperplane. So here I'm going to draw a vector that is perpendicular to this hyperplane. And this vector right here is equal to our W prime value, W prime. The perpendicular to our hyperplane vector is W prime. And we can see that because the vertical axis over here is positive. This is like a positive 1 value. So this is like the B component right here. Again, B from our picture up above, this B was positive 1. Happened to be in a similar location over here, but doesn't necessarily have to be that case. And then the X component over here, W1, right here. This is the W1 value, and that's like the negative 1 value. That's the slope of this line up here. So this W prime right here is our separating hyperplane. Being able to, in your head, translate back and forth between these two pictures is an important skill that will help you when we're visualizing a lot of these algorithms. Any questions just about what I have plotted right here?
Is the R on the bottom supposed to be the same as the other R?
The R on the bottom. I don't think there are any. These R's down here.
Yeah.
These are the real numbers. This is supposed to be the R like that, yes. So the space of real numbers in 2 dimensions is what we have for our prime version of these two vectors. The original dimensions plus 1. Yes, good question. Yes. Yeah, so it's a good question about zooming out to see both at the same time. And let's try to get it as good as possible here. So again, the things that I have in green right here, these are the two things to make sure that you fully understand about if you're plotting things this way, where the hyperplane goes through the origin and the axes are the like transformed axes, then the W prime right here is the point, the direction that is perpendicular to this hyperplane. Up here, this point right here, this threshold line has no direct intuitive relation to W. Similarly, I'll draw another perpendicular vector up here, do it in gray. This vector right here has no relation, no important relation to W. That point right here, not related to W. Point, not W. These are the two common mistakes that students make when visualizing things. Is you're thinking about this graph right here, and you think the separation point is W, or that the vector perpendicular to this hyperplane is W. That is not true. The W point is perpendicular to this hyperplane drawn where the axes are this transformation axis of X prime and W prime. Yes.
In the first graph, the horizontal is the initial W, right? The green.
This right here.
Like that length.
That length has no relation to W. You should think of this as being just a magic arbitrary number.
What does the box say?
The box says not W.
Oh, gotcha.
Inside of here, yeah. So it's the trade-off between zooming out and so being able to see two graphs at once versus the text becomes super small. But this, the only thing on this plot right here that is W is the slope of this line. The slope of this line right here is W. Over down here, the slope is not W. The slope or the W is this perpendicular vector. Yes.
So when we're plotting the purple plus and minus on the first graph, that is like the corresponding yi's in the data set, right?
The fact that I put pluses here means that in the data set, the y is equal to +1, yes.
Okay, and then sorry, I was gonna like read that. So then the y tilde is this diagonal line, even though we don't actually have the y-axis.
Yeah, the y tilde, so yeah, we've made up this imaginary axis. This axis here is not related to anything in the data set in any way. It's just something that we made up to add. And it's what this value, this formula right here, wx plus b happens to be equal to at each one of those points. Question is, the only point in this line that matters is where it intersects with the x-axis, and what matters is doing a lot of heavy lifting there. That's certainly the most important point. That's what we care about for doing the decision of is something going to be labeled by our algorithm as positive or negative, because this is the decision boundary. This point right here is the decision boundary that separates pluses and negatives. In terms of doing the actual classification itself, these other points up and down, they're not related to whether we're, they're not part of the algorithm per se. It's just this point right here decides whether we're going to be positive or negative.
Sorry, x is one-dimensional.
So yeah, the question is like this one dimensions here. How do we talk about the perceptron class in terms of the number of dimensions? And for linear classifiers, to the extent that we talk about the dimension of the perceptron itself, that is the dimension of this W variable right here, which is always exactly the same as the X because it's always an inner product between W and X. So here, this is a one-dimensional perceptron for one-dimensional data. Okay, good questions. I'm gonna pause first, or I wanna keep going for a second and say some more stuff which will answer a lot of questions that potentially people have about like, why do we care about this? So some of the properties here of W, some properties of W. And I'll specifically say W prime. So this is the vector version of W that has the bias, this B term right here, called bias, that has this bias interpreted. The first property of W is that the norm does not matter. Norm does not matter. So when you see norm of a vector, you should think like the size of a vector. So the size of this vector here does not matter. The only thing that matters is the direction. Only direction matters. And so this point right here is W prime. If I scale this W prime by any value, then the separating hyperplane stays exactly the same. The points that stay plus and the points that stay minus will stay exactly the same. That's only true if I scale W prime by any value. If I scale this W up here by any value, this W up here by any value, that changes the slope of this line and it causes me to have a new threshold, a new separation point. So these are two things that the textbook will say a lot and will come up in some of our problems here. So it's important to keep track that about which of these W's we're talking about. The norm of this W prime does not matter, so it doesn't matter how big it is, only the direction matters. Only changing this direction will change what this separating hyperplane value is. Let's see, let's change back to blue. In order to now help understand these, like, why do we care about this one-dimensional thing? How does this relate to the textbook? These pictures down here, I'm gonna redraw new data points, a new problem set in 2 dimensions, and we'll do it in this way down here, and we'll see exactly, try to visualize how exactly our W vector is related in what it's doing inside of this 2-dimensional space. I'll do that right here. So now we're going on to 2 dimensions. So again, both our x's and w's are in r to the d, but our x prime and our w prime are going to be, and that d is specifically equal to 2, and x prime and w time are in r to the 3rd. This style of plot right here is the type of plot that we're most interested in, but this is going to be very hard to visualize in 3 dimensions because we have an x1, an x2, and an x3 now. So when we draw these plots, when I draw this plot, I'm only going to draw the x1 and the x2 and not draw the x3. So I still have x1 and x2 up here. But now both of this x1 and x2, both of these actually come from the data. Unlike above, where x2 was always equal to 1, here x2 actually comes from the data. I'll draw out some points now. So we'll do positives over here, minuses over here, and a separating hyperplane. I think I've been using orange, so I'll do that in orange like this. Make it clear that it's not going through the origin. This is not going through the origin. And I'm gonna step away from the screen here for a second and try to visualize something with my hands on the board up here. Okay, so the x3 dimension is sticking out from this point, like it's coming out here. So positiveness is up here in this space, negativeness is into the board. And the x3 value for all of these points, is equal to 1. So all these points are really sitting at like 1 distance from the board up here. This line right here that I've drawn, this is actually not supposed to be a line, but this is a 2-dimensional hyperplane. Again, we're in 2-dimensional data points over here, so we're going to have a 2-dimensional hyperplane. And all these points coming out from the board, this line is like, it is going through the origin, at the board location here where this third axis is equal to 0, and then it comes out of the board up here. That's hard, understandably hard to visualize, but the important thing here, the one thing to make sure that like you take away from this is that this value right here, this is not equal to W. Every hyperplane, again, can be uniquely defined by a perpendicular vector. And so it's tempting that you see this line right here and you want to draw some sort of perpendicular vector to that line and call that the perpendicular vector that defines that hyperplane. But that is not what this perpendicular vector is. So this is not W. And this is not W in the same way up here that like this distance right here is not W. Going from the origin to whatever your separating hyperplane is, that is not equal to W. What W is something that we can't visualize here. But again, this is a two-dimensional hyperplane that's coming out like this, and W is somehow like pointing over this way. W is pointing over this way in this model, because this is a two-dimensional plane coming through like this, and perpendicular to that two-dimensional plane would be going like this. So it's hard to visualize, can't really draw it out, but the important thing here is that the perpendicular vector to your hyperplane, whatever that decision boundary is, wherever it's located, that is not W. Again, the properties of W that we observed up here, the two properties that we observed right here is that the norm does not matter, only the direction matters. In this sort of visualization, the norm does not matter, only the direction matters. We still have that down here. Only the norm matters, the direction does not matter. And the fact that the norm of this vector right here, which is not W, the norm of this vector does change that hyperplane. So that tells us that that cannot possibly be W right here. Again, W is sitting right here, pointing out of the origin where everything else is sitting up here with the Z value, the X3 value equal to 1. And no matter like how big this W is, it's going to be the same hyperplane. There are like decent visualizations of this on YouTube, but they use language that you're not ready to see yet. So in like a month or two, we will see some. We'll have all the language that you need for that, and we'll see some like good visualizations of this, and hopefully that will make more sense at that point. But again, important thing: make sure you understand this thing here, this distance. It seems like it should be W. It seems like this should be the thing that we care about, how we're measuring where our hyperplane is, but it is not how we're measuring where our hyperplane is. Questions? Yes. I'm going to pause you for a second. So the reason I'm pausing is because Ambiko is starting to use language that sounded like an algorithm of we do something to calculate W. At this point, we haven't talked at all about how to get W. This is just somebody gives us a W and we're plotting it. In just a little bit, we're going to talk about an algorithm that will get us W, but we haven't. You shouldn't yet be thinking about like algorithmically where does W come from. So I don't know if I cut you off too soon or.
Well, because we are using weighted quantitative. So, but then if you really want to find the hyperplane, okay, I'll just stop.
Yeah, so again, so it's admittedly very confusing wrapping your heads around all this because there's a lot of things that have to sort of come together before you can have any of it come together. But our hypothesis class is X into the sine of W transpose X, where W contained in R to the D. And at this point, I'm plotting arbitrary versions of these functions. Every one of these lines that I've been drawing corresponds to a different one of these functions. But we haven't talked about how to get this W. This is just like for some particular W, there is a line like this. For a different line, if I have Another plot down here, similar pluses and minuses. There could be many different hyperplanes. This could be one W. This is a good one separating them. This would be a bad one right here, a bad W. But the W value that corresponds to these lines is not the perpendicular thing. Yeah, sorry, go ahead.
So are all the points in this three-dimensional graph one unit out?
Yeah, that's a good question. So on this graph right here, on this plot right here, and on all these plots, the book has probably like a dozen of these two-dimensional plots in this chapter. All of these points are implicitly these are all implicitly three-dimensional plots where the circles and X's are at Y position 1, like out of the screen here. And this line right here, we're drawing just the two-dimensional slice here through this plane. But this line is actually a larger hyperplane that extends through the origin in every situation. Yeah. Sorry, Jay. Question is the difference between W and W prime, and it's a great question. And the difference is that W is how I've done it right here is W in this one-dimensional case is just has the exact same dimensions as X. So X is one-dimensional, so W is one-dimensional. Then we construct W prime from W by making it a two-dimensional thing that contains both the W and the bias, the W1 and the B. Similarly, X prime becomes X1 and a 1. And if we do that, it makes our notation a little bit simpler, that we can just write a single inner product for our W transpose X in our hypothesis class up here. Rather than writing a big summation of things. So the W prime always has, the only difference between W and W prime is that W prime contains a B in an extra dimension that's sort of artificially added. But it somehow contains all the same information, just in a different shape. This is a legitimately confusing thing because in the textbook, they will not do this like W prime versus W situation. They will use the same letter for both variables. In equation 1.1 right here, where they first describe the perceptron hypothesis class, they use W, which is going to be a D-dimensional vector. We know it's D-dimensional because this summation here goes from I equals 1 to D. But if you scroll down a little bit to their next definition of the same hypothesis class right here, we have the sign of W transpose X, where this W and this X, this W and this X, are the W prime and X prime that I've described here. So they describe this in words, what they've done as the transformation here. And it's sort of understood that like W is morally the same thing as W prime. Both of these two W's contain the exact same information somehow. We're just changing our notation to make things a little bit more convenient for us and forgetting to add those primes because it just makes more work to write stuff. So yeah, you'll have to, it takes a little bit of getting used to just understanding which version of these W's are they talking about, because you can only figure that out from context. It's not explicitly written. Good question. I need to keep moving on. So sorry, I realize there's more questions. Happy to talk about these things after class. Again, I'm never going to explicitly ask you about these pictures right here. The purpose of these pictures, though, is just to get you some intuition about how these plots of these hypotheses classes, these perceptrons work, and in particular to emphasize that even though you have learned that separating hyperplanes are uniquely determined by a perpendicular vector, that perpendicular vector is not the one that you think it should be just looking at the pictures. This perpendicular vector right here is not W and does not have an obvious relation to W. W is something that you can't easily visualize. Okay. I want us to, so yeah, I'm coming back over to the notes packet here, and we're going to talk about what's called the Perceptron Learning Algorithm next, PLA. So, we've talked so far about problem 2, defining the perceptron hypothesis class, visualizing the hypothesis class. We did a lot. That's what we did today, trying to understand that visualization a little bit better. And now we're going to come down here to problem 3, working with the PLA, which is not the People's Liberation Army like you're all thinking. It is the Perceptron Learning Algorithm. The notation here in the textbook I find to be a little bit awkward, but the notation is that, there's my writer. The notation is that we have an iterative algorithm similar to PageRank, where W of t plus 1, so the t plus 1 iteration, t is our current iteration, equals W of t plus y of t times x of t, like this. So this is a much simpler iteration than in the PageRank algorithm. There's only 2 computations going on here. We have a scalar multiplication right here. Scalar multiplication. And in addition, all of these W's, basically anytime from now on where we see W's or X's, all of these are what I was previously calling W prime. These are the D plus 1 dimensional vectors. So the runtime of all of these, the runtime of everything for addition or scalar multiplication is D plus 1, which equals theta of D. Again, the X is in R to the D plus 1, and the W here also R to the D plus 1. The T over here is, again, the iteration number. There's the rest of this problem is walking you, well, let's see, the thing that I find awkward about this notation is just the fact that they're using parentheses here to put in the t plus 1, like the current iteration. These W's and Y's and X's, they are not functions where this t value is being passed as a function. Instead, these are all like the value of this vector at this iteration, or the value of the X data point at iteration t. Yeah, in the PageRank paper, they used superscripts for this. Yeah, nothing else to say about that update formula. The important thing, first thing you should always be thinking anytime you see an update formula is get a sense on what is the actual runtime there. So that's what we did here, computing that runtime of theta of D. Exercise 2 right here. I'm going to jump over to the textbook for a second and come down a little bit to this right here. Throughout the textbook, there are a handful of exercises in the middle of the text. My expectation is that you would be able to do all of these exercises. Some of the exercises I explicitly provide as like, I don't know, in the notes packet. But my expectation is that you can answer every exercise in the book. As you can complete every exercise in the book. And so some of those I will call out in the notes packet as being particularly important, but some of them I won't. This particular exercise right here, so it says you have a couple of proofs on broken down into three parts right here. All of the proofs here are just all proofs are just like 1 to 2 lines applying a definition or basic linear algebra fact. So I'm not going to do this exercise 1.3 in class right now. That is going to be for you for homework. And again, I'm not going to collect it, but it's the sort of thing that you would be responsible for on the exam. I might ask you to just prove one of these things for me while explaining the perceptron on our next exam. Questions about the equations up here or what you're expected from exercise 1.3? Okay. Problem, this part, part 3 right here, this is getting into the more interesting stuff. And there's going to be a handful of things that we will do in class. I'm going to make the font size, bump it up again. There's going to be a handful of things that we do in class that I will be expecting from you that are not directly related to anything in the textbook, or the textbook rather assumes that you're able to do all of these things without explicitly spelling them out. And this is the first example of something along those lines. This is the sort of problem that I think is particularly important, again, so particularly important and not explicitly covered in the textbook, not explicit in the text. So, problem 1.3 at the end of the chapter. So in this textbook, problems are things at the end of the chapter. Exercises are things in the middle of the chapter. My expectation is that you're able to do all of the exercises, but I have no expectation about any of the problems unless I specifically mention them. Problem 1.3 at the end of the chapter proves that the total number of iterations t required for the PLA to converge to an optimal solution is given by this formula right here. You are not required to understand the proof of this formula. So in this class, we won't complete that problem and prove this bound. You're not responsible for that, but you are responsible for just knowing this bound and understanding what it means and how to work with it. So the first thing, anytime you see these like crazy formulas like this, is to try to illustrate those quantities. So we're going to illustrate both of these quantities and see what they mean. This Greek letter right here is pronounced rho, and this quantity right here is called the margin. We will see the margin very often in this class. The name of this Greek letter is rho, R-H-O, pronounced rho. And rho, I'm going to draw our data set like this. Do a different color for the pluses and minuses. And I'll even do an extra plus and an extra minus like that. And the axes here, so this is a two-dimensional, d equals 2. So our x and w are both contained in r to the 2, x prime, w prime, contained in r to the 3. This is my x1 and x2 axis, but again, all of this stuff is like it's 1 unit out from the page right here, floating in the middle of the air. And our separating hyperplane, let's draw it in gray, like this, not necessarily through the origin. And here you'll notice that I have a star on the w. This is W star. The actual, the distance from the origin to the this perpendicular part right here. So I'm going to redraw this so it's farther away. Sorry for that. Like that. That part right here, that is not W. That is not W. There's no direct way to visualize W on here. But so this vector, this perpendicular vector right here, not W, but still we label this whole hyperplane as being W star because it is somehow defined by W star. but it is not this hyperplane right here. It is not this vertical or this perpendicular value right here that defines it. Anytime you see a star on a variable, what that star means is that it is somehow the best variable, the best version of that variable. So the star, you can see the green star means best somehow. And in this case, the perceptron learning algorithm is guaranteed to give us a separating hyperplane at the end of it, and this W star is the final output of the perceptron learning algorithm. So in this case, in particular, W star must be a, and I'll put it in quotes again here, separating hyperplane, where separating means that it actually does a good job. It perfectly separates the pluses and the minuses. The actual values that we're trying to visualize here, this margin, this row value, is the minimum distance between the hyperplane and one of these data points. So this distance right here, that distance right here is rho. The minimum distance between a data point and the separating hyperplane. If you think about the linear algebra, that's what this mathematical equation works out to. The intuition behind it is the minimum distance. So this is the rho value right here. I'll do a black line under here. I'll do this whole thing in black just to emphasize that this distance right here is related to that. This R value up here is called the radius. Go dark blue. Let's change a different color because I'm already using blue for something else. We'll try orange, even though that's really close to red. This is right here is called the radius, R for radius. There is no reason why rho, like mnemonic, why rho is for margin. It's just rho, this P looking thing makes an R sound. It's always called the margin. The margin is always with this rho letter right here. The R for radius makes more intuitive sense. But the radius of a data set is if you draw a circle around your whole, whatever your biggest data points are, that circle, that distance is the radius. So it's the size of your biggest data point. That's what this is saying over here, is that it is the size of your biggest data point, is the radius of the data. Or yeah, it's the radius of the problem, the radius of the data, or just the radius. I've got a lot of things to cover, so I apologize, I'm not going to stop for questions here. But we can see that the runtime here depends on this R value, this rho value, and this W star value, which cannot easily be visualized. This W star right here cannot be directly visualized. Because it is like popping out of the screen on this like third dimensional axis. But what we can see is that if our margin value is larger, so if there's more distance somehow between the pluses and the minuses, that will make this rho value be larger and the algorithm will converge faster. If our data set is somehow larger, this R value up here is larger, that will make our data set converge slower. And so this gives us some properties about our data that can help us understand, will this PLA algorithm take a long time to converge or not a long time to converge? Again, the textbook states this, does not do any of this explanation about trying to visualize these quantities. It's just expected that you, if you see an equation like this, that you're able to create your own visualizations about what's going on. Moving it, so that's part A right here. Part B, what is the overall runtime of running the PLA? So this is something that's not covered at all in the textbook. Again, supposed to be obvious. But anytime you have one of these iterative algorithms, you have an iterative algorithm, the runtime is going to be the runtime per iteration times the number of iterations. We talked previously when we wrote out the equation for the perceptron that the runtime per iteration is going to be theta of d because it's a very simple thing, only has a single scalar multiplication in it and a single addition. And then the number of iterations is the formula that we had up above. This is a big O formula because it's an upper bound. O of r squared w star squared. Oftentimes when I'm writing out vector norms, I find it convenient to just put a single bar instead of a double bar to make things more legible when I'm handwriting them. And then divided by the rho squared. And so multiplying these two things together, we get it that our overall runtime is d times r squared, blah, 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 w star squared over rho squared like that. Good question. And the question is that theta or O? I forgot to write out exactly what it's going to be. Here we have theta, which is an upper and a lower bound, and O is an upper bound. And so we combine these two things together, we get an O as the result. Intuitively, the reason why this is going to be an upper bound and not an exact bound is because up here, we're just, this is the maximum number of iterations that it could take. If our initial guess of our W value is perfect, like we somehow accidentally guessed that our initial W was a separating hyperplane, then there's nothing anymore to do, and we will get the final result instantly. So vast majority of the iterative algorithms we'll see, the total number of iterations is just an upper bound, and yeah, not an exact bound. It's a worst case bound. Let's see, last problem here, we'll do really quick, start talking about, so what are some of the differences between the runtime analysis for the PLA and the PageRank power method algorithm? The main one here is that the PLA is an exact algorithm. PLA is exact. We have a formula for exactly how many iterations we need to do in order to get to the final result. We have a formula for number of iterations to get an exact result. That is, we get a W star that does separate the data, that separates the data. Separates the data. PageRank, in contrast, PageRank is an approximate algorithm or an approximation algorithm. Approximation algorithm. And maybe more technically correct is that PageRank itself is not an algorithm, but it's this framework of using the top eigenvector. So the power method, or the exponentially accelerated power method, these are approximation algorithms. And they're approximation because we only have that between, say, WK plus 1 to WK. We have some sort of bound on those. But we're never going to eventually get to the correct answer. We have to run for an infinite amount of time to get to the correct answer. Next time and subsequent classes, we're going to talk a lot more about these approximation algorithms or approximate algorithms, and we will start talking actually about things that are probably approximately correct. So that'll be a fun buzzword to get to. That's it for today. I realize there's a lot of questions. I had to keep going when people have your hands up. Happy to stick around and get those questions answered, or if you have some other questions about the exam and pagering stuff in particular, not about the things that we talked about today, happy to stick around and get those answered as well. But that is it for today's class.